Data visualization using graphics in bar. Data visualization within R can be done using a variety of different graphics, and they all have pros and cons and are all useful for visualizing data in different ways. And different data should be visualized in different ways depending on what you're trying to present. We can use bar charts, pie charts, histograms, kernel density plots, line charts, box plots, heat maps, and word clouds. So the first one we'll focus on are bar plots. Bar plots are horizontal or vertical bars used to show comparisons between categorical variables. They represent length, frequency, proportions, any type of categorical value you can think of. The syntax is simple, it's just the bar plot of what you're trying to graph. So if we were using the MTCars dataset intrinsic within R, let's say we wanted to look at a bar chart of the counts by gear. So here we're pulling the table, MTCars, the gear column, into a vector for counts, and then we're creating a bar plot which shows the counts, whether it has 3, 4, or 5 gears. We could also use the horiz command, set to true, to flip the bar chart over and make it horizontal. And so you can see the x-axis on the first graph is the number of gears, and the y-axis is the count. If we flip it to a horizontal bar plot, the x and y are inverted. Now we want visualizations to be meaningful and appealing, so the one way we can do that are including things, as well as understanding that data, to include titles, legends, and colors. So let's say we did the same thing. We created a bar plot of counts, but this time we create a header, a title for the graph called simple bar plot. XLab is the X label called improvement. YLab, which you can't see on here, will show as frequency. And then you see this tiny box in the right-hand corner is the legend, which is the row names to specify. And then we specified the colors as red, yellow, and green. Now we could also build a stack bar chart. So here we're doing a count of gear again, but we're also including VS. Again, we create the title, which is the main for car distribution by gears and VS. The X label is number of gears. And for the columns, we decided we'd have gray and cornflower blue. And the legend has those row names. And so you see the 0 and the 1 is the VS, which ends up equating to the total gears. So the counts are still the same, but the stack bar chart is now showing that distribution in regards to how many of the VS within gear 3 are 0 and how many VS within gear 3 are 1 or blue. Instead of stacking it, we could do group bar chart as well. So we're doing the exact same thing, except at the bottom, you can see we've added this legend for beside equal to true. So instead of stacking them now we can have them right next to each other. Now a pie chart has generally been frowned upon in the business world the past few years, but things tend to cycle, and sometimes pie charts are still very valuable. So a pie chart's a graph in which a circle is divided into sectors or segments, each representing a proportion of the whole. So you can think generally of a proportionality out of 100%, usually. So when we look at this syntax, well, pi and the different attributes that we have within it. So let's consider a pie chart that contains the values 10, 12, 4, 16, and 8 as slices. And those slices are denoted as the US, the UK, Australia, Germany, and France. And those are the labels. So here, we create slices concatenating 10, 12, 4, 16, and 8. We have the labels as US, UK, Australia, Germany, and France. And then we have the pie as the slices with those labels attached. And you can see to the right that those numbers are denoted to match what the labels reflect. Well, let's say we wanted to make it a holistic percentage instead. So we still have the numbers, but this time let's create percent. So we'll say round slices divided by the sum of the slices times 100, which will produce the percentage because we're adding all those numbers together, and then dividing by the proportion and multiplying that times 100, which will give us the proportion or percentage out of 100. You can see here we have the labels, so we have the country. After that, you have double quotations with a space, which will denote a space on that label, and then the percent, which is the actual amount, percentage, with the percent sign. The other thing we did here, so that new piece, we've added rainbow 5, which will allow for different colors. You could also create a 3-dimensional pie chart. For this, you have to import the library Plotrix. Loading that library, again, we've done the exact same thing. And then you can see in the last few lines, we're using the function pi3d, again with the slices, those numbers, the same labels, and then the explode, which is that depth. Our third visualization are histograms. So histograms are used for distributing a continuous variable and the frequency of values, generally by binning or bucketing those values into ranges. So the difference between a bar chart and a histogram is a histogram will have all of the bars touching visually. Now let's say we wanted to create a simple histogram using the mtcars dataset. Well, the first step is to bin. Now binning is a common term used in machine learning, which is essentially grouping, right? And so let's say this is miles per gallon. Well, we don't want a single bar for every single unique miles per gallon, because that means a car could have anywhere from 0 to 70 to 100, which would mean 70 to 100 different bars. So what binning does is clusters or groups these ones together and then count how many fall within each group. So when we graph the histogram of mtcars, you can see what this distribution tends to look like. It applied the x-axis in intervals of 5. And so you can see that the majority of cars get 15 to 20 miles per gallon. Now, to make it more visually appealing, all we did was add the color dark green. The other thing that you can do is use the break command, which can control the number of bins. So R automatically attempts to compute where breaks should be and how many should fall into each of these groups, or the optimal placement of where those breaks are. But you can either specify the count of the number of breaks, or you can specify the exact numbers of where you want breaks to occur. So you could have the breaks specified at 12, 17, 31, and 40, if you wanted to. Now a kernel density plot shows the distribution of a continuous variable. Syntactically, we're looking at plot density of what we're trying to graph. And so one important thing to note is that the histogram is not a great method for determining the shape of a distribution, because a histogram depends on the number of bins that are used. So to facilitate or aid in this, kernel density plots are used over histograms. Well, what do they look like? They look like a distribution. So if you've heard of the uniform or null distribution or Poisson distributions, if we use a kernel density plot, we can essentially look at what the data is telling us to look at what the distribution looks like. So here, if we use mtcars again, we're using a density plot of the miles per gallon, and you can see here that it's a pretty normal distribution, except with a longer tail or higher tail on the right side around that 30 point. We always want to visualize and make things prettier. Most leadership wouldn't want to see this if they could see this. It's just more visually appealing to the eye. So here, again, we created this density, we created this plot. Again, we have the main, which is the title of this visualization, called kernel density of miles per gallon. And then the polygon is essentially filling in what's under the curve. And so we're saying we want that to be sky blue and the border of that to be black. Now a line chart is very extremely frequently used, often with forecasting type data or longitudinal type data. And a line chart is used to represent a series of data points connected by a straight line and helps visualize data that changes over time. So what does that look like? Well, we wanted to create a line chart using the plot function by plotting body weight against months. So we create a vector called weight, and we have these different values within it, from 2.5 to 8.1 at the end. And we have our months vector starting at 0 going through 9. And so what we're wanting to do is plot the months by weight. Now the type is a function that allows you to see or to visualize the data in different ways. So with this type, you can see that they're dashed lines with circles, but you can have connected lines, dotted lines, etc. There's a variety of ways that you can manipulate that type. Main is baby weight chart. So we're calling the title of this slide, of this visualization, baby weight chart. Our X lab, our X label is months, and our Y lab is weight. If we wanted to make it a little more colorful, here instead of COL, we're using color equals red. So box plots, whisker diagrams, or box and whisker plots are all synonymous, and they display the distribution of data based on 5 different number summaries. We have the minimum value in the data, the first quartile, the median, the third quartile, and the maximum. Now, if you've ever heard of IQR, that's the interquartile range, and that's looking at the difference between the first and the third quartile. So if we want to graph a box plot, this is what it looks like. We're working with R's built-in data set, air quality, another very common one, and we're graphing ozone. So we're calling the title of this slide, mean ozone in parts per billion at Roosevelt Island. The X label is parts per billion. The Y label is ozone. Note that all of these are always in quotations. And we set horizontal to true, otherwise it would be up and down. The first line you see near the 0 point, that's the minimum. The darker line that's connected to the dash is that first quartile. The line within the box is the median. The line to the far right of the box is the third quartile. And so you see this box is the interquartile range where the majority of ozone falls within. And then that far right line is the maximum. And those 2 red circles you see have fallen outside of the norm maximum range when R computed it. And so those 2 are denoted as outliers. If we want to change the color of the box, all we do, again, is use the COL function and set it equal to green, or whatever color you'd like. R allows for all colors, including hex codes, so that you can specify as you see fit. R also allows for color combinations, so it will automatically group sets of colors together. Now, heat maps are a 2-dimensional representation of data in which the values are represented by colors. There's 2 types of heat maps. We have simple heat maps, and that provides an immediate visual summary of information. And then we can have elaborate heat maps to understand complex data sets. So let's see what this looks like. Here we have a heat map with absolutely no labels, and we're using the CLF package using heat map spread small. This doesn't really tell us much, right, because there's no labels because we don't have information. So let's label the columns and rows. And the labels can be numeric or cell arrays or strings. And so you can see now we have an X and a Y axis. The X's are numeric from 1 to 15. And the Y are these labels for small. WashUse, Ayer, Rolfav, etc. Bloomingdale. Now what's often common for heat mapping is density or geographic type data. So if you wanted to see, let's say, movement within Walmart, you could have IoT sensors throughout the store tracking where customers go and where they spend their time. And by the amount of time they spend in an area, the heat map could be a darker red. And if no customers go to an area, it could be white. And that would allow Walmart to identify where customers spending the majority of their time. Should they have other product placements near that area because most customers are going there? What is most important for those customers in those areas? Lastly, we have word clouds. So word clouds highlight most commonly cited words in text using quick visualization. This is often done in combination with natural language processing from a visualization type perspective. So what this looks like is this on the right. So we need to install the package word cloud, load the library word cloud, and then we're going to read in this CSV file called text.csv, which includes a variety of text. Set the header equal to true, and then we're looking at the head of the data. And so from the word cloud, the actual function that we're running here. So we're saying within the column, within the data set data, and the column word, we also want to get the frequency of those words. We want to include only words that have a minimum frequency of 2. We want to include maximum number of words as 100, and we can choose whether we want to randomly order these words or not. Now, the black is obviously a little difficult to read and look at, so a lot of time word clouds will integrate color as well as a variety of rotations. So here we have the same piece, except for these last 2 lines. So that rot.per at 0.35 is the number of words that are rotated in horizontal versus vertical schemas. And then the colors, like I mentioned before, where instead of just specifying green, you can use something like BrewerPal and say, I want 8 colors total using the Dark 2 theme. And so these 8 colors within this visualization come from Dark 2. And there's about 30 different color combinations that fall within BrewerPal. Now, let's go through an example. So, a real estate company is planning to launch apartments in Boston City and needs to analyze the factors affecting the price. And so the following data is available. So you have this data on the number of rooms in a house and then the average price of houses in the hundreds of thousands. So this available data should be visualized to understand the interpretations easily. Well, graphics in R can be used to visualize that data. So, how about we create an X and Y scatter plot showing the correlation between the number of rooms and the average price of the house and see what that looks like. So we graph that. So we have the number of rooms in a dwelling on the x-axis, and you see from this group it ranges from 4 to 6. And then the price of a house in hundreds of thousands seems to be on the lower end around 100,000, 120,000, and goes up as high as about 240,000. And so these dots essentially represent the x and y points for each of these. So 4.3 will be associated with 14.7, 5.0 with 18.9. And so it's plotting each of these dots on this graph, on this scatter plot. And then it's creating a line of best fit. And so this line of best fit is showing that there is an upward trend in regards to the number of rooms in a dwelling tends to increase the price of a house. Now that makes sense because we know that generally the larger a house, the more expensive it is, and the more rooms that it does have. We could also visualize this via bar chart. So let's say we grouped or binned the number of rooms and had a low, medium, and high group, and we had the price of the house on that y-axis. Well, based on how we binned it, we see that prices of houses in the low group versus the high group are significantly different. Now there are graphical limitations to base R. Firstly, plots can't be saved as objects. Second, multivariate exploration is complex. Multivariate meaning multiple variables put into the same model instead of just X on Y. We might want to look at multiple variables and how they impact something visually. Layering or layers are not supported, and we can't merge graphics. So, to overcome these issues that we've faced with base R, a package was created called ggplot2.